Our goal is to find the maximum number of non-overlapping sets from a list of candidates. To do this efficiently, we are going to represent the logic of the problem through binary arithmetic. Elements A through F map to 6-bit binary positions, from A on the right to F on the far left. Candidate sets convert into unified bit masks. Set 1's A and B become 000011. A used mask tracking our algorithm's state starts at 0. Converting these sets into binary strings transforms the search. The computer can now treat the problem of identifying overlaps as low-level mathematical comparisons. The process begins by evaluating our first candidate, set 1, against our current history. A bitwise AND compares set 1 to our history mask. A 0 result proves no conflict. We add set 1 to our solution and update the mask. Testing set 2 gives a non-zero result because both share a bit in the second position, element B. A non-zero result indicates overlap. We cannot include set 2 on this branch. Continuing down this path, we take set 3 since it fits. We then reject sets 4 and 5 due to shared elements, completing our first path with a score of 2. Reaching the bottom of a branch provides a baseline. We know 2 is achievable, but we haven't yet proven it's the best possible result. To find the global optimum, a tree structure tracks our decisions. Each set is a fork to either take or skip. We backtrack to explore new combinations, removing set 3 and reverting the used mask. Now we follow the alternative path, skipping set 3. On this branch, we evaluate set 4 against the current mask. Because we use bitwise comparisons, the overlap check is instantaneous. The resulting bit mask shows a 1 in the far right position, element A. Thus, set 4 is incompatible and must be rejected. By systematically exploring these skip alternatives, the algorithm ensures that every possible combination is eventually considered. As the search tree grows, we need a way to ignore branches that can't possibly improve our score. Imagine we are on a branch where we have only taken one set, and only one candidate remains. We calculate an upper bound for this branch. Adding the one remaining candidate to our current score of 1, the maximum possible value is 2. Since our current record is already 2, this branch cannot improve our solution. We immediately prune this branch. Pruning prevents the algorithm from wasting time on thousands of unnecessary comparisons. This is what allows branch and bound to scale to complex problems that would otherwise be too computationally expensive to solve. The algorithm continues this process, using these bounds to navigate the tree until every pathway is either exhausted or pruned. When the search finishes, the system confirms the optimal value. Here, we found 2 distinct ways to reach our maximum value of 2. This method works by combining 3 pillars: bitwise AND for instant conflict checking, branching to explore the search space, and bounding to prune dead ends. Bitwise arithmetic makes the overlap check fast, while branch and bound ensures the search remains efficient. It is a fundamental strategy for solving combinatorial problems by making the computer work smarter, not just faster.